So we're going to expand the single slit diffraction to double slit, and then further to more slits, which is the makeup for a diffraction grating. So starting with single slit over here, this was the expression that we came up with. So we are going to operate on the double slit by just modifying the limits of integration. So instead of single slit now, our limit of integration will be from having the slit arranged in this manner, whereby this is the central axis. So this would be the slit separation. B here would be the slit width. So we will be then integrating from negative B plus A over 2 to negative half of A minus B, and then add to another term here, which is taken from A minus B over 2 up to half A plus B. Okay, so it's really very simple. And but in this case, I've written here just like the single slit here, we only wrote down the amplitude component. The time function here of the wave, we just drop it first because we are interested in the irradiance. So by integrating and substituting the limit of integration, so integrating exponential ik sine theta ds will give you exponential ik sine theta divided by ik sine theta, which we already factor out over here. So we still have this term here and this term, and that leaves us by putting in the limits. We have exponential half ik negative A plus B sine theta. Here will be half k ik negative A negative B sine theta, and so on. This will be from this term here. Okay. Then in order to simplify, we then going to substitute for half kb sine theta with beta, half ka sine theta with alpha. And this is equation 2. Now, what we're going to do when you substitute this in, so we take an example for this one, which you can work out for the other 3 terms. Now, half Ka A plus beta sine, A plus B sine theta, you have half Ka sine theta represented by alpha, half Kb sine theta represented by beta, so that leaves you I alpha plus beta. So similarly for the other 3 terms, that's how we come to these terms here within this square bracket. But what about this term here? What we do is we divide this denominator, we multiply by 2b over 2b. So that will give us half kb sine theta represented by beta, and that's how we get the function 2I beta, and the b here goes to the numerator. And here we factor out, expand it, multiply that out, you get exponential negative I alpha multiply exponential I beta minus E negative I alpha multiply with E negative I beta, and so on. Now over here you find that this is common. This is common for these 2 terms here. So we factor it out, and that leaves this one and this one here, and then that leaves this and this over here. And this term and this term, they are common. So we again factor out, and that gives us this term written here, EI alpha plus, or rather this common term is written here, and that leaves us exponential I alpha plus exponential negative I alpha. So we have these 2 terms here. Okay. And then what we're going to do is we're going to use Euler's equation to substitute for these terms here. So we have a cosine alpha plus I sine alpha plus cosine alpha minus I sine alpha. This one is cosine beta plus I sine beta minus cosine beta minus and minus become plus, so plus I sine beta. Now, looking at this expression here, you'll find that this term and this term cancels out, and then this term and this term cancels out. That simplifies very much to just 2I sine beta 2 cos alpha, which is this and this. Okay, so we regroup them. Then we have 2 ELB over R0, and then we then have this term here, this 2 and 2 cancel out, so we are still left with 2, so 2 is still here. So we have sine beta or beta, which is that sinc function, and cos alpha. Now, for this is the electric field amplitude, then writing in terms of irradiance is squaring this and multiply by half epsilon 0 c, because this ray is traveling in air, so using this term here. So then we have squaring of this term, squaring of this term, squaring of this term, multiplied by this factor here. And we then expand this squared term of 2 here, become 4. Now this 4 factor will be special. Afterwards we're going to explain. So leaving all this term here. So therefore now we have the irradiance term from double slit diffraction, which will be given by, now for this term and this term, we will then represent it using I0, which is the maximum irradiance. And then this term here, the sinc function for beta squared, is actually what we obtained for single slit diffraction. And cosine squared alpha was what we obtained previously from double slit interference. This was how the irradiance vary. So which means that now it is a combination of the diffraction and the double slit interference. Now the factor 4 here tells us that the maximum irradiance from the double slit now is 4 times that of the maximum from the single slit, because single slit was given like this. So if we ignore this double slit interference term, just looking at this term here, so it's 4 times that of this. But of course, we have the interference term, don't forget that, for this double slit diffraction. So rewriting this by alpha, we substitute back in what we have used in the simplification. So half Ka sine theta. Now, K is 2 pi over lambda, so that gives us then, this term here becomes pi a sine theta over lambda. And comparing this with what we obtained for double slit interference term, it was given as 4I0. Just look at the cosine term, the variation in the intensity given by the cosine term. It is pi a over lambda, which we have here, sine theta. But here it's y over L. But sine theta was the angle, inclination angle of the point that we're observing with reference to the center axis. And then on the screen there, that will be a distance, lateral distance y, and L would be the distance from the slit to the observation screen. So just now, the earlier part, we came up with an expression for double slit diffraction. So we had that single, this is the interference term, which was similar to what we consider for Young's double slit, and this is due to the single slit diffraction. So single slit diffraction, the sinc squared function is represented by this dashed curve here, whereas this interference term, cosine squared alpha, is represented by this full line here. There's lots and lots of peaks here. So you have these fringes. And the maximum here, as you can see, occur at every multiple of pi. There's a pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. Whereas for the diffraction, the minima occurs also at integer multiples of pi, when beta is equal to integer multiples of pi. Now this one here, where you can see that this diffraction minimum, the first minimum here, falls on the 6th pi of the interference term. So with this, when you multiply the two terms, basically this maximum here will go missing because it's multiplied by 0. So this interference term order will go missing. Now, why is it occurring at 6? Because we have actually chosen this example from the double slit dimension given by the fact that the slit separation is 6 times that of the slit width. A is equal to 6b. All right, so capping effect of capping of the interference fringes by the diffraction term will result in something that looks like this. And you find that this peak here, the maximum intensity, becomes 4 times I0, as we mentioned earlier on. And here is what you will see on the screen. You see a bright central maximum for single slit, but when you put a double slit, then you find that within that central maximum, there will be interference pattern here. Okay. So this is coming from, it's a combination of diffraction and interference due to double slit. Now, diffraction minima occurs when beta is equal to integer multiples of pi, or when you have this condition being met as m lambda equals to b sine theta. Whereas interference maxima, not minima, maxima occur when alpha equals to p pi, whereby p is also integer positive or negative 1, positive or negative 2, and so on. Or when the condition for p lambda is equals to a sine theta, where a is the slit separation, b is the slit width. So when diffraction minima coincide with interference maxima, as I've shown you just now, the fringe will go missing, the interference fringe will go missing. So what would be the condition when that happens? That is when, now rewriting this as a sine theta is equal to m lambda over b, sine theta is also p lambda over a. So we equate the two because they're supposed to coincide. So we equate the two, and that will give us condition for missing order when a is equals to p over mb, or when alpha equals to p over m beta. So this is achieved when the slit separation is a perfect integral of the slit width. So here we have a equals to perfect integral of the slit width. So in the example, previous example is a equals to 6b. And the missing orders, therefore, will occur when p is equals to 6, 12, and so on. So multiples of 6 because of this. Ready to go to extend it to more number of slits, which would actually make a grating. So in our double slit, this was what we did for double slit, redrawn here. But now we want to extend the integral to include over up to n number of slits. So how do we do that? So we use this basis. So what we do is we will identify each of these slits by an index j, so that the resultant amplitude for multiple slit ms here would be expressed by, of course, in this case, I've written back the wave function here, the oscillating part. So we are going to sum up the contribution of all the slits. So whereby we will take it as from, because we are taking summing half the slit from the top and half from the bottom. So that's why it will be enough if we take for j from 1 up to n divided by 2. Okay, so we will have it an expression that will be summing from negative 2j minus 1 a minus b divided by 2 up to negative 2j minus 1a plus b divided by 2. And likewise here will be, because b is fixed, whereas a here will be extended as we go further from the central axis for those slits that are further away. So this 2j minus 1a plus b divided by 2, this is 2j minus 1a minus b divided by 2. So we expand from this to this. And the first integral represents the jth slit, which is just below the origin. And the second integral here represents the jth slit above the origin. That's why we use n over 2, as I said just now. Now, if we were to represent the integral, this term here, within the curly bracket by a factor, by a symbol k, to make it easier, we just focus on that. So we then expand this integral. This is what you're going to get. So we integrate exponential, you have 1 over k, ik sine theta, exponential, substitute this inside for s, yeah, and you do it for the other terms. So you have equations 12. And again, we simplify further by substituting the term beta and alpha, just like what we did for the double slit. And therefore, now we can then write this factor here by b over 2i beta, whereas the terms inside here, we do away with the sine theta and the k and b and ka, and so we use beta and alpha, and you can try it out in detail on your own, but it will then simplify to this term here, and then we factor out the common terms. This is what we get, and finally this is even more simplified. So we have the exponential I into 2j minus 1 alpha plus exponential negative I into 2j minus 1 alpha multiplied by this factor here, which is e I beta minus e negative I beta. And we have b over 2i beta here. So that's equation 13. Okay, next. Now, if you were to put in Euler's expression, substitute Euler's expression into this, represent this by cosine 2j minus 1 alpha plus I sine 2j minus 1 alpha, then you'll find that it can be further simplified to just 2 cos 2j minus 1 alpha multiplied by 2i sine beta. Similar to what we did for the double slit, diffraction for double slit consideration. So now this term cancels, and we have simply 2a sine beta over beta, taking the real, this happened to be, cosine of this happens to be the real part of the writing in complex form, exponential I 2j minus 1 alpha. Now, referring back to the summation term, which was here, referring to this summation, summing it up. And okay, so we need to find the sum of k from j equals to 1 to j equals to n over 2. So if we take represent the sum as s here, so we sum up the real part of this within here, sum up all the terms here, because this is constant, so we sum up all these terms here. So what we have is, if you were to expand it out, then you have taking the summation of this will just give you exponential I when j is 1, 1 minus 1 is 0. 2 minus 1 is 1, sorry. Exponential I alpha plus the next one will be 3 alpha, 5 alpha, and so on until n over 2 minus 1 alpha, summing up to n over 2. Now, this bracketed series here is a geometric series. The first term is ei alpha, and we represent by a, but this a is not the slit separation, so it's not that term. And the constant ratio of successive term, this divided by this and this divided by this, is exponential I2 alpha, and is not equals to 1. So therefore we can write the summation term. So the sum of the geometric series can be written as a into Rn minus 1 over R minus 1 if R is larger than 1, we write in this term. So in other words, now the geometric sum of the previous equation then will turn out to be, that's the summation of this will turn out to be, now R is exponential I2 alpha to the power n over 2 minus 1 over exponential I2 alpha minus 1. So this will turn out to be exponential in alpha minus 1. And this one we move to the denominator, which will be this term divided by that. And if you look at this, what we have now would be this. If you divide by this, you get exponential I alpha minus 2I alpha minus alpha. When you divide this, you get exponential I alpha. When you divide 1 over this, you get exponential negative I alpha. So this is a term that we have. Now, we can then rewrite this using Euler's representation. Here, what we do is substitute this complex term with cosine and the sine function. So we have this. This will work out to be 2I sine alpha. So in the end, what we have would be, divide this term by I, it will turn out to be I cos n alpha minus 1. Okay, we have a negative sign here now. Minus I cancel, so after division, then you find that this is negative sine n alpha. You can work it out. Okay, now if you take the real part of this, it will give you here the real part is actually sine n alpha divided by 2 sine alpha. So which tells us then, because there's a 2 here, 2 and 2 cancels to give you b sine function, sine beta or beta, multiplied by sine n alpha over sine alpha. Okay, then we insert back into the electric field at point P. Electric field of the light that arrives at point P. Then we will substitute that summation term by what we just worked out here. Here, S term, substitute that back in here. So this is what we have. In terms of irradiance then, we will look at only the amplitude. So squaring of this multiplied by half epsilon 0 c, because the light is traveling in air. So we're using epsilon 0 here. That will give us squaring of this term here. We have a b here, so ELB R0 squared, and this sinc function squared, and sine n alpha over sine alpha term is also squared. And we can then sum up this term, represent this term instead by I0. Okay, so then it will look like this, whereby this again represents the diffraction term from single slit, and this would be the interference term for n number of slits. And this expression is valid for all n's, whether it's odd or even. Now, for single slit diffraction, you just put n equals to 1. For double slit diffraction, then of course n is equals to 2. Let's now look at the interference term. This interesting interference term here, sine n alpha over alpha squared. When alpha is equals to 0 or m pi, then it is indeterminate, because it becomes 0 and this becomes 0. So, however, we can show that it can produce a maximum using L'Hopital's rule. For any m equals to 0 or plus or minus 1, any integer multiples of pi, then what we have here is sine n alpha over sine alpha, taking the limit of alpha to m pi. That is equals to n cosine n alpha over cos alpha, also taking the limit of alpha to m pi, and it will give you plus or minus n. So this is the explanation of using the L'Hopital's rule. Now, for this rule to hold, one of the requirements is the limit. That is, for the limit of taking x to c, so you have the derivative of this function, which is a derivative of sine n alpha, that gives you n cos n alpha. Derivative of sine alpha will give you cos alpha. So in this case, it's easier because this becomes 1 and 1. So that's why you have the n here. So this limit must exist. So it does exist. So that's why we have this term here. Now let's look at it graphically for an example whereby we have taken n equals to 8. The sine n alpha function against alpha in units of pi. Over here you can see units of pi. And this black one is a sine alpha against alpha, also in units of pi. Okay, so then this is what you're going to see. Okay, and if you square it, squaring the function, squaring this and this will give you this term. So what I did was I superposed this up here so that now you can see that squaring of this will give you 2 peaks here, and squaring of this initially there's only 1, 2, 3, 4, 5, 6, 7, 8 peaks. Now you have double that. Okay, 2, 4, 6, 8, 10, 12, 14, 16. Because any parts that's negative will then become a positive value. So this is how it's going to look like. But we are dividing this by this. So what are we going to get? So for this particular function, trying out for n equals to 8 through Excel, you can try it out yourself. This is what's going to result by taking the ratio of sine n alpha over sine alpha against alpha plotted. This is in units of pi. So this is how it varies. And squaring this, so all these squared terms will then flip to positive. So squaring that will give me 1, 2, 3, 4, 5 peaks here within this range here. And all these little mini maximum, which we call them the secondary maximum. These big peaks here, large peaks here are called the principal maxima. So this is the result. Therefore, at alpha equals to multiples of pi, integer multiples of pi, you'll find that, if you look at this, you'll find that the squaring of this ratio actually give you a value which is equals to n squared. Now, I told you that I was using 8, n equals to 8. So you can see that the peak all takes a value of 64. That definitely show us just now the L'Hopital's rule that we consider is holds here. And that's the result that we get. Now, when we combine the diffraction and the interference term, now that was just due to the interference term just now, right? Now we are doing, if we combine, we multiply, get the product of the diffraction interference term, what it does is that this interference term will then cap all these peaks, and all these peaks will then be very little. This is what you're going to get. Because in this case, we've taken the ratio of A is equals to 3B. Okay, A equals to 3B. The slit separation is equals to 3 times the slit width. So this will be, these dark lines, the full lines will be the resultant irradiance variation due to Fraunhofer diffraction from, in this case, 8 slits with a ratio of A equals to 3B. Okay. So principal maximum occur when this function is equals to n. Okay, that is when alpha equals to multiples of pi. Or if you want to write in terms of sine theta, when sine theta is equals to multiples of lambda over a. Integer multiples of lambda over a. For the secondary minima, so that was the principal maximum, secondary minima that comes from the interference term again. What we have here is The interference factor is equal to 0, minima, when this function is equal to 0. But not when when the denominator is 0, because when the denominator is 0, then we will be getting the maxima, isn't it? So this happens when alpha equals to p pi over n, where p is integer up to n minus 1, and beyond. Now these are the minima. Example, for n equals to 8, then we have p will be from 0 to 8, and the numerator will go to 0 when supposedly when alpha equals to pi over 8, 2 pi 8, 3 pi 8, 4 pi 8, 5 pi 8, 6 pi 8, 7 pi 8, 8 pi 8. But at alpha equals to 0 and at alpha equals to pi, this corresponds to the first two principal maxima. So hence, therefore, the secondary minima will occur when p is equals to this, but not equals to 0, plus or minus n, plus or minus 2n, because the principal maxima will occur at this condition. So you will find that there will be n minus 1 minima occurring in between the two consecutive principal maxima. And with n minus 1 minima, there will be n minus 2, one less secondary maxima, which you can see. Here is for 8, so we have 1, 2, 3, 4, 5, 6, 7 minima, secondary minima, and 1, 2, 3, 4, 5, 6 secondary maxima. Now, the secondary maxima will occur between each pair of principal minima, and that will be located at points where sine n alpha has its greatest value, or when n alpha is equals to half integer of pi. So that will be equal to 3 pi over 2n, 5 pi over 2n, and so on. But no secondary maxima will occur when alpha equals to 1 pi, half pi over n, or at any 2n plus 1 pi over 2n. If you look at this in detail, we have used n equals to 8. So we have pi over 8 here for all the minima, but the secondary maxima occur at 3 pi over 18, 5 pi over 18, but it doesn't. You don't have a maxima at secondary maxima at pi over 18. Neither do you have one at 15 pi over 16. That's because the principal maxima overrule that. It is actually masked that out. Yeah. So summarizing it, the maxima and minima are described by using a general function alpha equals p pi over n. P can take this integer number. So the condition for principal maxima occurs when p is equals to 0 plus or minus n and plus or minus 2n. Condition for secondary minima when p is all integer values other than those in this condition. Condition for secondary maxima now. Secondary maxima will occur when it is odd multiples of half of pi over n, except when it is equals to plus or minus pi over 2n, plus or minus 2n plus 1 pi over 2n, and so on. And this is how it looks like on the screen. If you have single slit, double slit, you see this one starts to show interference pattern, and then you start to see the secondary maximum in between the principal maximum, and then more secondary maxima appearing, and then the principal maxima will start to narrow and the intensity will then rise further because it's proportional to n to the power of 2, n squared. So all this will then, conservation will then be pushed into irradiating, giving light over here, add up to the intensity there. So for large n, the multiple slit pattern is bright and very distinct. And the principal maxima occurs when PON equals to multiples of P. Therefore, you'll find that the condition for principal maximum is just simple. Alpha equals to m pi. M is integer number. But you have alpha equals to half Ka sine theta or pi A sine theta. So therefore, the condition for the principal maximum can be rewritten as pi A sine theta over lambda equals to m pi. See, alpha equals this. So substitute this pi cancels. You have m lambda equals to A sine theta. So this is a diffraction grating equation where m is the order of diffraction, but this is valid only for normal incidence at the grating. Now, why are the principal maximum very distinct and bright as n gets larger? You remember it narrows, the principal maximum narrows. So if we look at the irradiance, it's given by this term, right? So, and we know that the principal maxima, that's a peak occur when alpha equals to m pi, and taking the limit, this term here is equals to n to about plus or minus n. So squaring that, you'll find the irradiance at the sharp piece increases as squaring of n. So this increase then would be accompanied by overall decrease in irradiance between the peaks, between the peaks of principal maxima. So the secondary maximum get more and more suppressed because conservation sort of all this irradiance then goes into these narrowed peaks. So which means that a grating which has many slits, like for example, you can have a grating like how many grooves or slits, like 1,200 slits per mm, as good as that, or even better. So they can then, in that case, they can produce brighter and narrower principal maxima. So that's very useful when we use it to disperse, like in spectrometer. All right, this is the final part. We are talking about diffraction grating. And if you look at this, just now we came up with an equation that represents diffraction grating, which is valid for normal incidence. Now, what if it is not at normal incidence? For example, here it is. This is the incident beam coming to. This is just showing two slits, but this represents the diffraction grating. It's coming at an angle of incidence theta I, and then diffracted angle is theta m. And here we have the slit separation, which slit separation here. So in this case, the diffraction grating equation will have to include the diffracted angle, which is A into sine theta I plus sine theta m equals to m lambda. So where m here then stands for the diffraction order, and theta m is the angle of the mth order of diffraction. So I'm going to go very simple, not so much in detail. That's why I said brief introduction here so that you can have an understanding. So what happens is that when you have a beam of light coming, so you have this at the center line, optic axis line here that passes through the center here. So you find m, this order is 0, and on the top and bottom it is 1 and -1, and as you go further you go to higher orders. Now just looking at this, just representing this converging lens over here. So after these are the range wavelengths that are diffracted of different orders, M1, 2, and 3, whether it's on above or below the axis or on the left or right of the axis, depending on our reference orientation. Yeah. So assuming that this may be white light, for example, so we would have dispersion as well. So the first order, the spreading will be short. As you go to higher order, the spreading of the component colors become wider and then wider. And you find that as it go to high order, as it spread wider, it tend it can overlap with the previous previous order. So then we then define what we call the free spectral range. So this actually refer to the non-overlapping wavelength range of a particular order. So it would be the maximum wavelength separation that can be unambiguously, now this is wrong spelling here, no B here, resolved in a given order. For example, this would be the free spectral range of order M, and that will be given by lambda 1 over M. So what is lambda 1? Lambda 1 would be the shortest detectable wavelength in the incident beam. Okay, so this will be shortest wavelength that can be detected. Then we talk about this. I'm just giving you some terms that we talk about when we're talking about grating, some figure of merit. So when we talk about dispersion of a grating. Now, if you look at this, higher order diffraction grows less intense, isn't it? So wavelengths within the higher orders are better separated, but they grow less intense. So then if we say they are better separated, then we are going to ask a question: what would be the angular dispersion? That's the angular separation per unit range of wavelength, and that will be written as m over a cosine theta m. Okay, this is a diffracted angle of mth order. Now, at the focal plane of the lens, we can define then a linear dispersion, which is just simply the angular dispersion multiplied by the focal length of the lens. Okay, where y here would be the distance along the focal plane. Let's say we have a focal plane here. Okay, so then we will talk about the extent of this, which the linear dispersion, so the linear expanse of that. And then we can define a plate factor, which is the reciprocal of this. So I'm just giving you terms and definition. Now, increased dispersion does not mean that the neighboring wavelength will appear more distinct, unless those peaks themselves are very well and sharply defined. So then we talk about the ability to produce distinct peak of very closely spaced wavelength, what we call as resolution. We use a term called resolution. Just now was dispersion. Now it's just now was dispersion. Now is resolution. So we talk about resolving power of that grating, and that is given as for lambda divided by the minimum closely spaced difference in the wavelength. What would that be the minimum that they can resolve? So that is equals to order multiplied by n, that is the number of slits, and this is given by w sine theta m over lambda, where n is the number of lines in the grating, w is the rule grating width, that means the grating has got a width with all the rules. So what is the extent of that? So that will be equals to a slit separation multiplied by n multiplied by the number of lines, that will give you the width of the rule grating. Then we talk about blazing. Just now we said that at higher orders, then the intensity drops. So if we want it to be better dispersed, well separated, but then unfortunately the intensity drops. So how can we overcome that? So this is one way of doing it. So what we do is we then incline the surface of the grating at certain angles. So we call it as blazing of the grating. So by blazing it, what happens that if it's a transmission grating, that means light passes through and it gets diffracted on the other side. So let's say here the beta equals to 0 or order here, the diffraction maximum occurs at m equals to 0 when there's no blazing. And then when there's blazing, this beta gets shifted. This diffraction maximum gets shifted. And if you remember, we have the on the top and bottom, we would have the order, so which means that we can now shift the maximum intensity to a higher order. So that's after blazing. For reflection grating, that's like falling on it and then it get reflected. One example of that would be if you were to take a CD, because there are a lot of grooves there, you shine a laser light on it, you find that you get the diffracted dots or beam at different order. You can try that out yourself. So here, what they do is also by blazing, what happens is that you're going to shift the diffraction maximum to a higher order so that you can get, you want the better separation, which is occurs at higher order. So you can overcome the drop in intensity by shifting the diffraction maximum. So that's the end of lecture 17. Thank you for listening.